Now we're going to take a look at inverse trigonometric functions. If you recall, when we introduced functions, for a function to have an inverse function, the original function has to pass the vertical line test. The horizontal line test. So first of all, for any function to be a function, it has to pass the vertical line test. And we see with all, like here we have the sine function. If I draw a vertical line anywhere, it only passes through a single point. So every x is mapped to exactly one specific y. In order for the inverse to be a function, it has to also pass a horizontal line test. Otherwise, that function's inverse would not be a function once we found its inverse. If you recall that if we folded it across the y equal to x, that's what the inverse functions look like. And so they kind of end up going vertical. They're a vertical, I would say, they're a vertical relationship to the original. So what you see originally, it kind of looks the same way, but going up the y-axis rather than the x-axis is kind of what happens there. So at any rate, in order for any function to have an inverse that is a function, it has to pass the horizontal line test, and we can see it doesn't work here. So in order for us to have an inverse function, we have to limit the domain. And so this is another one of those times where we would limit domains on functions if we want to do special things with them. Like here, we want to look at the inverse function. So we say, okay, let's limit sine to going from negative pi over 2 to positive pi over 2. With that restriction, only going from negative pi over 2 to pi over 2, then this becomes a one-to-one function, and hence its inverse would also be a function. Every x would also have one y for the inverse. So the inverse function, y equal to sine of x, is called our inverse sine, and this is specifically for the sine function. So the most direct, or sometimes for short, it's called the arcsine function. Remember that we limited the domain between negative pi over 2 to pi over 2, and we reflect this across the graph for y equal to x. So as we reflect it across this line here, what we see is the domain of the arcsine function is between negative 1 and positive 1, and and then the range goes from negative pi over 2 to pi over 2. Whenever we have an inverse function, the x's and y's simply switch places for the inverse function. So notation-wise, here's how we can denote the arcsine or the inverse sine function. Sine minus 1 of x means the sine of y will equal x. And so my inputs, x, as we saw on the previous slide, go from negative 1 to positive 1. So that's my new domain. And then y will be somewhere between negative pi over 2 to positive pi over 2. And can equal those at either of those ends. So the arcsine of negative 1 gives me negative pi over 2, and the arcsine of positive 1 gives me positive pi over 2. So we read this as y equals the arcsine x, or y equals the inverse sine at x. And when you think about inverses, think about stuff that undoes other operations, right? So like division and multiplication, those are inverse operations. A multiplication will undo a division, and a division will undo a multiplication, or can. And so in a sense, we are undoing a sine operation when we take the arcsine of a number between negative pi over 2 and positive pi over 2. Okay, so there's our domain, and here's our range expressed in a different way, obviously, for the inverse sine function. So let's look at some specific examples here. The first one says, let's evaluate the arcsine of root of 3 over 2. So we're going to do that first. And just as a reminder, right, we have our unit circle, our quadrants here. And if we remember where sine was positive in the first and the second quadrant, because sine is the y value, and y's are positive above the x-axis, and both those quadrants are above the x-axis. So they both produce positive sine results. So looking at this sine of root 3 over 2, we know that's one of the results of taking the sine of a couple of angles. And so, and because it's positive, we know that there would be a sine that would result in root of 3 over 2 here and here. But this is where we have only limited our domain to these two quadrants here and here. So because we've limited the domain of the original sine function, if it's positive, it's going to be in the first quadrant, and if it's negative, it would be in the second quadrant. Because remember, sine would also be negative over here. And so we've eliminated two of the quadrants, one of the other positives and one of the other negative quadrants. So when I see a positive arcsine, I know that the angle I'm after is the angle that'll be in the first quadrant. Therefore, the arcsine of root 3 over 2 is going to be pi over 3, or 60 degrees. If this had been negative root 3 over 2, the arcsine of negative root 3 over 2 would have been negative pi over 3. Remember, we're trying to stay within that boundary of the original domain for the sine function, which is between negative pi over 2, so going in this direction, or positive pi over 2 going in that direction. Okay, well, what about the arcsine of negative 1/2? So again, it's negative, so that tells me that's in the fourth quadrant. And we know that sine, the y, for negative 1/2 is going to be negative pi over 6. The negative pi over 6, the sine of negative pi over 6 would give us negative 1/2, and therefore that's the arcsine of negative 1/2. If it had been positive, this would be positive pi over 6. So for sine, it's either positive angle or negative angle. For C, the arcsine of negative 3, well, we have to remember that the domain for our arcsine is from negative 1 to positive 1. And so negative 3 is outside of that domain of values. And so this is not allowed. This would be the empty set. There is no solution for that particular arcsine value. Let's talk about the inverse cosine. Cosine, again, if we wanted to have or to find a inverse function for it, we need to pass the horizontal line test. And so we run into problems back here. It's going to clash with here. And once we've done this, we've gone from 1 to negative 1. That's kind of we've hit all of the major points. All the values, both positive and negative, have been touched at least. And so we are going to restrict it to 0 all the way to pi. My function is restricted differently. We can't do the same as we did before, negative pi over 2 to pi over 2. It would only give us the positive results. And so we go from 0 all the way up to pi. That'll give me both the positive and negative results for cosine. So we restrict the domain to 0 to pi. It's a 1-to-1 function, and then its inverse will also be a function. So with the restrictions on the domain for the original cosine function, 0 to pi for our angle, we see how this is the flipped version If we flip it across or fold it across this line y equal to x, these points line up. They basically switch spots. We have 0, 1 here, 1, 0 here. We've got pi negative 1 here and negative 1 pi here. So we take care of all the positive and the negative values associated with x and y. And we call this the inverse cosine or arc sine function. And the graph is obtained by reflecting the graph for this restricted domain 0 to pi about the line y equal to x. So the y equal to arc sine of x means the cosine of y will equal x, where x, of course, will be between negative 1 and positive 1, right? So we're talking about the domain here of our inputs, and what would be the output here of just the regular cosine function. And then the range, the y, is going to be the 0 to pi, again, what would be the values that we would take the cosine of, somewhere between 0 and pi. So this reads y equal to the arc sine or inverse cosine of x, and the domain of the arc cosine is from negative 1 to positive 1, and the range is 0 to pi. Keep in mind that in the quadrants here, if we're looking at cosine as points on a unit circle, the x values, that if we're only going from 0 to pi, cosine is positive here and negative here. Now, it's also negative here and positive here because it's the x values, but we're leaving these out because we can't have, for an arc sine function, more than one outcome for any one outcome for any one input. And so if you think about the cosine function and the sine function itself, it basically goes from negative infinity to positive infinity. So we would literally have an infinite amount of outputs for every single input if we didn't limit the domain here. All right, so looking at a couple of examples, we'll start off with the arc sine of root 2 over 2. Root 2 over 2 is my 45-degree angle. That's what gives us that. And this is positive. Didn't mean to actually do that. But thought I had my pointer here. So this is a positive root 2 over 2. And so that's going to be in the first quadrant. And so the arc sine of root 2 over 2 is pi over 4, which is 45 degrees in radians. For the arc cosine of negative 1/2, now we have a negative, so we know it's in the second quadrant. And it's negative 1/2. And 1/2, we know for cosine, is 60 degrees. So in the second quadrant, that's going to be 120 degrees, or 2 pi over 3s. Let's see, pi over 3 is 60 degrees, or pi over 3. And if we go 2 pi over 3s, we go another 60. That's 120. Notice 120 also has an angle that goes back to this axis here, the reflective axis, that's pi over 3 or 60 degrees as well. 3 pi over 3s give me 180. So we're taking one of those pi over 3s away, leaving us with 2 pi over 3. And notice this falls within the acceptable range for the arc cosine and the acceptable domain of the original cosine that we restricted, 0 to pi. Now let's take a look at the inverse tangent. The inverse tangent follows the same restrictions as sine. Tangent, remember, of a function, of an angle, is sine of that angle divided by the cosine of that angle. And so that's why we ended up with pi over 2 and negative pi over 2 as being asymptotes, because that's where cosine is 0. Cosine is 0 at 90 degrees and negative 90 degrees, or pi over 2, negative pi over 2. So if we restrict it, remember when we look at the tangent function, it really just has a bunch of these. We start again at pi over 2, and then we go to 3 pi over 2. We have the exact same graph. So really we're just taking the graph of tangent, folding it across the line. And for the inverse functions, the vertical asymptotes are actually going to be horizontal asymptotes. Let's take a look at that. We can see here that it looks a little clumped together here. There's a lot going on. The inverse function for tangent of x, we restricted it from, this is the regular tangent, negative pi over 2 to pi over 2, is the inverse tangent or arctangent function, and the graph is obtained by reflecting the graph of y equal to tan of x with restrictions from negative pi over 2 to pi over 2 about the line y equal to x. And so we can see here, here's in blue our regular tangent function, and then in red our new function. Notice that the tangents now, not the tangents, the asymptotes are horizontal asymptotes rather than vertical asymptotes, but basically we do a similar thing here. So y equal to tan negative 1 of x means tan y will equal x. So x now is unrestricted from negative infinity to positive infinity. The y outcomes will only fall between negative pi over 2 and pi over 2. Looking at the negatives and the positives, we keep in mind the tangent is positive here and tangent is negative here. Tangent is also positive here and negative here, but we're eliminating these two, and we're only going to say from positive pi over 2 to negative pi over 2 for our outcomes. We're going to restrict ourselves to those values. We read it as y equals the inverse tangent or the arctangent at x. And the domain of inverse tan at x is from negative infinity to positive infinity. In other words, we can plug whatever we want in there. We're not restricted. Remember, cosine and sine are restricted between negative 1 and positive 1. Tangent has no such restrictions. But the range here, because of the restrictions we had to put on the domain, my range is restricted for the arctan. So let's do some examples here that involve the arctangent. And I always like to keep in mind what tangent represents, because it does help remembering where we get some of these results. Tangent is the sine over cosine. And so when we talk about the arctan of 0 that we have here, we have to think about the only way I could get 0 for tangent as a result is to have sine be 0, right? 0 divided by some number, in this case it would be 1, is where tangent of an angle will give me 0 as a result. And the only place that happens where sine is 0 but cosine is not is here at 0. Well, yeah, 0 degrees. If I'm not moving anywhere, cosine is 1, sine is 0, the y value is 0, the x value is 1. And so the tangent, the arctan of 0 is 0. And it's 0 degrees or 0 radians. For the arctan of negative square root of 3, and I always like to think of those that are whole like that as being over 1, because it can also help me draw a picture. I know it's negative, so I know it's going to be down here in this quadrant, and we can think of it as a triangle, keeping in mind the SOHCAHTOA thing, S-O-H, ka, toa. The most important for us right now is the toa part. And that means opposite over adjacent. So for the arctan of negative root 3, that would be here, negative root 3 over positive 1. Thinking about this angle, those would be the two legs of the right triangle. So I could take 1 squared plus square root of 3 squared, and that would give me my hypotenuse squared. And that would be 1 plus 3 for our hypotenuse squared, which is 4. And if we take the square root of that, we get h is equal to 2. So this is 2. So we can think of it in terms of, well, what angle gives me root 3 over 2 for the opposite over hypotenuse. Opposite over hypotenuse. So in other words, what angle is sine root 3 over 2 and cosine 1/2? The answer for that is the 60 degrees, or, pi over 3. But it's negative because we also have the negative output. We're in the fourth quadrant there. In evaluating the other three reciprocal functions, you guys know with tangent, we have the cotangent, and we're going to restrict it the same as we do the cosine function from 0 to pi, much like the cotangent function has its hypotenuse. And our x inputs are from negative infinity to positive infinity. For the inverse cosecant, we're limited, just like we are with tangent, from negative pi over 2 to pi over 2. For the secant, which goes with cosine, 0 to pi. But y cannot be pi over 2. Y can't be 0 here with the cosecant, and y can't be pi over 2 with the secant because our values are undefined at those points. To remember which ones have which restrictions, one of the things that we can do is to remember what's in the denominators, right? So like with cotangent, sorry, get my pen here. Cotangent of an angle is cosine over sine. And so with that graph, we're restricted wherever sine of an angle is 0. Sine of an angle is 0 at 0 and pi. And so that becomes part of my range / domain restrictions of the original cotangent function. Remember that cosecant actually goes with sine. The cosecant of an angle is equal to 1 over the sine of an angle. And so its restrictions are the same as sine's restrictions. Sine's restrictions go from negative pi over 2 to pi over 2. And so remember, at 0, we have a problem because the sine at 0 is 0, so we can't have that. And the secant, is related to the cosine function. And so we have its restrictions the same as we do for cosine. So for the cosecant, our restrictions are the same as sine. For the secant, our restrictions are the same as cosine. For the cotangent, we make its restrictions similar to where it's for the original function where the asymptotes are. So I'm finding the arc cosecant or the inverse secant of 2. I always like to relate it back to what the reciprocal function would be, right? And for cosecant being 2, that would be the equivalent of sine of theta of our angle being 1/2. With sine of our angle being 1/2, the reciprocal of that would be 2/1. And we know that sine of, or the angle that gives us 1/2 for sine is 30 degrees, or pi/6. This is positive 2, so we know with the restrictions of cosecant being from -pi/2 to pi/2, so we're only doing it in these two quadrants. Of course, with the positive, obviously, it's going to be in the first quadrant, so pi/6 rather than -pi/6, which is what it would be if it were in the other quadrant. Using our calculator with arc sine and arc cosine and all these type of things is something we do or can do with any number, really. But there are just ones that we're already familiar with that we can give the exact values rather than decimal approximations. So when we can, we'll do that. But if we're using our calculator, you'll notice that above the sine, cosine, and tangent buttons, you actually see the arc sine, arc cosine, and arc tan. So we have to hit second sine, and that'll give me the arc sine, second cosine, that'll give me arc cosine, etc. Now, there are no arc cosecant, arc secant, or arc tan. In fact, there are no cosecant, secant, or tangent, cotangent buttons either. So, but we do have that, the cosecant is really just the reciprocal of sine. So when I'm calculating a cosecant, I can, after I find the value, I can either use some calculators have a 1/x button you can just hit. It'll flip it and it'll give you the reciprocal. Other calculators have x to the -1, it's just really, the same thing. So depending on your calculator, you'll have one of those two buttons. So if in taking the arc sine, I simply take the x value that we're given, put it under 1, so hit x to the -1 or hit this button, and then find the arc sine of it, that will give me the arc cosecant. And the same is true for secant. Take the value of x, hit x to the -1 or 1/x, then take the arc cosine, that will give me the secant value. Now, with these two functions, they have the same range and domain, right? Their domain and range values, we restricted tangent to -pi/2 to pi/2. Cosecant has the same restrictions. We restricted cosine to 0 to pi. Secant shares the same restrictions. With tangent, it's a little bit different. Tangent is from -pi/2 to pi/2, but cotangent is from 0 to pi, because with their graphs, that's where the asymptotes are. And so we just use those. So with tangent, we have to be careful because of those different range and domain values. If the x value that we're evaluating for the arc cotangent, if it's positive, so it's greater than 0 or it's equal to 0, then whatever we find by going 1 over that value and taking the arctan is the correct value for cotangent because it's in the first quadrant. But if we go 1 over x and we take the arctangent and it gives us something that's negative, meaning somewhere between 0 and -pi/2, then we have to add pi to it to get the correct value. We can take a simple look at what we have. Tangent was positive here. Tangent is negative here. But for, the same is true for cotangent. Cotangent is positive here. But for cotangent, we take the negatives over here. So if I have a negative value that I'm inputting into arctan, this will give me whatever angle I have. If I add pi to it, it'll just move that same angle into the other quadrant. So I could just add whatever this comes out to be plus pi, and I'll have the value that I want here. And so that's what we have to do, so that cotangent's negative values end up being in the second quadrant rather than the fourth quadrant. So using our calculators here, we can evaluate the inverse sine, the arc sine of 0.75. Now, one thing you have to make sure is that your calculator's in radian mode. So usually if you go to the mode button, you can scroll down until you find the choice between degree and radian. Make sure it's set to radians. Then exit out of that, clear your screen, and we're going to take the arc sine, so second sine of 0.75. That's a positive value, so we expect to get a positive result. And we see y here is equal to 0.8481 if I rounded it to 4 decimal places. I like to go out a few decimal places here when dealing with these. All right, now here's an arc cotangent. So again, we're going to use the arc. This is a positive one. So if I go 1 over that, right? So if I go 2.8, and then, or I just put 1 over 2.8, or I type 2.8 and I hit x to the minus 1, I get the tangent equivalent of the cotangent value. And now I use the arctan for this value. But try to avoid rounding, just as a good rule of thumb. And we see that y is equal to 0.3430, and this was started out and ends as a positive product, positive number, and so therefore I can just keep this. But when it's negative, like what we have here, again, negative 2.3, and we're going to take the reciprocal of that because it's a cotangent. We want to find the arc tangent, so I take 1 over that and then hit arctan of that number. You should get y equals negative 4.101. To that, I need to add pi, because remember with cotangent, it goes from 0 to pi, and it does not go into the negatives. So we got to add pi to that. Oops, sorry, I have my decimal in the wrong spot there. It's like, this is still going to end up negative. Let me just rewrite that. 0.4101. So we're going to, and it's negative. Add pi to that. And try to use the button pi because it's not rounding it to 3.14. That'll give you a little bit more accurate answer, 2.731. That is also in the second quadrant. And so therefore that is our value, or our answer for the arc cotangent of negative 2.3. Now, because of the restrictions we have on the domain, we do have to be careful when we're using inverse functions to pay attention to what those restrictions are for the parent functions and then hence the inverse functions. Because typically when we see opposite operations occurring, or inverse operations occurring, that the answer tends to be whatever you started out with, right? Usually if we take 3 and then we multiply by 2 and then turn around and divide by 2, we just end up back up at 3. And that's kind of the idea with sine and arc cosine. But remember, because of the different restrictions in the domain, we do have to be careful about that. And to make sure that, especially if we're switching from one function to another, like cosine to arctan or things like that, that we're taking that into consideration as well. So let's take a look at like number A here. Number A, I obviously mean letter A. If we took the sine of negative pi over 8 and then took the arc sine of that, would we still be at negative pi over 8? And for sine, we have to think about where is the restrictions on arc sine for sine. Where's the restrictions on arc sine? And the arc sine goes from negative pi over 2 to positive pi over 2. And so negative pi over 8 falls into the fourth quadrant. And so we know that the arc sine then is just going to undo the sine that I have, and we'll still be at the same angle there, negative pi over 8. On the second one here, we're taking the cosine of 5 pi over 4. 4 pi over 4, one less than that, would be pi. So 5 pi over 4 is adding one more pi over 4 there, which puts it into the third quadrant, outside of the arc sine range of outcomes. And so what would the arc sine be of 5 pi over 4? We know that if we take the cosine of 5 pi over 4, we get negative root 2 over 2. That's what we get there. Cosine is negative in the fourth quadrant. Everything except for cotangent and tangent, in fact, are negative in the third quadrant. So then we have to take the arc cosine of that. But cosine is relegated to just the first and second quadrants, 0 to pi. And so we have to think, what is the angle that would give us a negative root 2 over 2 for cosine in this quadrant, because this is the quadrant where cosine is negative for arc cosine. And we know that that's going to be 1 less. So this, let's see, at 180, we're at 4 pi over 4. If I want this to be the same angle here, 45 degrees, pi over 4, I actually have to take 1 pi over 4 away, so minus a pi over 4, and that leaves us with 3 pi over 4. Notice that 3 pi over 4 is 3 45s. That leaves us with one more 45 that would have taken us to pi there. And so the arc cosine of negative root 2 over 2 is 3 pi over 4. In the quadrant where the range of outcomes is allowed for the restrictions that we put on the original cosine function. Let's do a few more of these with the cosine, tangent, and the directions here are asking us to find an exact value. Now, we don't necessarily need to know what the angle actually is in order to take the cosine of an arctan. If we know where the angle is, we can use Pythagorean Theorem to find the other side, and hence we'll be able to find the exact cosine. Let's try a couple of these and see how we do. So the first one here is a tangent of 2/3. The arctan, of 2/3. That, of course, would give us an angle that we're taking the cosine of. So what is the result of the tangent? So if we're taking the arctan of 2/3, remember tangent is, for this one is positive, and so that's either going to be in the first or the fourth. That's going to be some angle here that gives us this triangle. And tangent is opposite over adjacent, TOA, opposite over adjacent. So 2 is here, 3 is here. And so using the Pythagorean theorem with a right triangle here, the two legs, that's 2 squared plus 3 squared equaling h squared, my hypotenuse squared, or you could put c squared. So that's 4 plus 9, which is 13. And so h is going to be the square root of 13. So I know this, square root of 13, and I know I want to take the cosine of this angle that we really don't know. Now, we could find out what the radian or the degree measurement is approximately, but it doesn't really matter because we wanted to get an exact value anyways. I know that the cosine of this is adjacent over hypotenuse. Again, So TOA, adjacent over hypotenuse. So this would be the cosine of that theta is going to be 3 over the root of 13. Adjacent to the angle and the hypotenuse, root 13, which we would need to rationalize, get rid of that square root in the denominator. That leaves me with 3 square roots of 13 over 13. And it's positive, which we expected because tangent and cosine share that angle as far as where the positive outcomes go. Let's take a look at the next one. We're having an arc cosine of something negative. And we know cosine is negative in the third quadrant, right? And so, I'm sorry, not the third quadrant. I mean the second quadrant. And that's a restriction on cosine, the arc cosine, right? So negative 1/4, that's going to put me here, where the adjacent over hypotenuse would be negative 1, so negative 1 here, and 4 would be the hypotenuse. Using the Pythagorean Theorem, for that, that'd be 1 squared, which is 1, plus b squared equals 4 squared. And so b squared will be 16 minus 1. 1 squared is 1. So that leaves me with 15 for b squared. So b is equal to the square root of 15. So the height here is square root, and it's 15. It's the arc sine of the negative. We know cosine. We take the negatives into the second quadrant. And now we're looking to find the sine of this. The sine is opposite over adjacent. So the opposite is the square root of 15. So we have square root of 15, and that's positive. Sine is positive in the second quadrant there, over the hypotenuse, which is 4. Keep in mind one key difference we had in this problem here. In these problems, we took the arc tan and the arc cosine first to get essentially what would be the angle that we would then take the sine of and the cosine. Arc cosine and arc tan and arc everything else are the ones that have the restrictions. So those are the ones where we have to go, wait a minute, am I in the right quadrant, right? And once we've decided where that arc tangent or arc cosine's quadrant is, then we just take the cosine of whatever it's in. Sine, remember, arc sine was relegated to the first and the fourth. But I didn't need to rewrite this because I was just taking the sine of whatever angle this is. I can take the sine, the domain for sine is any real numbers. So there's no restriction on what I can take the sine of and what I can take the cosine of. But with the arc tan and the arc cosine, those have to come out in certain quadrants because they can only have one. If we were to find every quadrant that cosine could equal negative 1/4 or tan could equal 2/3, there would be an infinite number of them, technically. Cosine is both negative in the second and the third quadrants. We would still have negative 1, just our negative, the square root of 15 would be negative as well, going down. But with the arc cosine and the arc tan, we know that it has to be, for cosine it had to be in the second, and for tan it had to be in the first. Okay, let's take a look at a application problem here where it involves angles. We've got over here in a corner, we've got a security camera that is going to make a certain angle, depending on the length here, of a counter with jewelry in it that's 30 feet from here to here and 10 feet, so a total of 40 feet. But we drew a right angle in here so that we could break this into two different triangles and use tangent. So if we look at this as one thing here, 30 divided by, this would be my opposite over adjacent, right? The two legs of the triangle. This would be my opposite over adjacent here for the second triangle. And we're told that the angle through which the camera rotates to scan the counter is given by this equation here. Question then is, find theta to the nearest degree if x is 10 feet. So if x is 10 feet, if it's 10 feet away, what's going to be the angle that this camera would scan? So this is really just a matter of plugging this in here. Theta, the combined angle is going to be tan inverse of 30 over 10 plus arctan 10 over 10. So really, we have the arctan of 3 plus the arctan of 1. Now, because it's asking to the nearest degree, we'll find both of these individually. I'm going to round it to a couple of decimal points, and then at the very end, I'll round it to the nearest degree. Just because I have 2, I don't want to round and then round a second time. So with the arctan of 3, putting my modes back into degrees, we get 71.57 degrees. And then we have the arctan of 1. Which gives me 45 degrees. That's actually a known one. And then adding these two together, that's 45 plus 71.57, which gives me 116.57. 57 degrees, or rounding it to the nearest degree would be 117 degrees. And that would be the total angle measurement, this one being the 71.57, obviously the larger one, and then 45 back here. The combined theta of both of those is about 117 degrees. So with these, I highly recommend as you're doing these, draw out the triangles. You don't have to use your calculators unless it's kind of a problem that makes you use your calculators, like they give it to you as decimals. On a lot of these, you want exact answers rather than decimal approximations.